Hello everyone. Today I'm going to talk about my research on sparsity-promoting algorithm for the discovery of informative Koopman Invariant Subspace. My name is Xiao Pan, and this work is done by me, and my advisor is Professor Duraisamy. This work is funded by DARPA, LRFL, and NSF. Traveling wave-like structures are everywhere in fluid mechanics. For example, on the left shows the process of laminar to turbulent transitions, where one can see multi-scale structures from strict to fully turbulence are traveling downstream. The right video shows the turbulent mixing layers, where shear layers develop downstream, unstables, and break down, then finally diffuses. These wave structures are important in understanding the nonlinear multi-scale dynamics of turbulence. But first, can we extract these wave structures from data, then properly analyzing them? To answer this question, let's first take a look at the overview of data-centric engineering for fluid mechanics. The traditional approach either take the simulations or the experiments to obtain observables, measurements on the full field data, then then these data are further interpreted by human experts. Now, to answer the previous questions, we want to obtain physical insights of the wave structures from data. This falls into the topic of model analysis that links between the data and the physics. When we're talking about the model analysis, there are many different methods coming out of my mind. In general, depending on how much they refer to the operator of Navier-Stokes equations, they can be divided into operator-based and data-based. For example, resolvent analysis separates the linear operator from the nonlinear operator within the governing equation. Navier-Stokes governing equations, you can derive the resolvent operator from governing equations. Well, the only thing you need is base flow. While POD simply only considers the linear projections and most efficiently preserves variance in the data, and no governing equation is needed, so it can be applied to a wide range of dynamical systems. There's an intersection between them called Koopman operator analysis, where we learn Koopman operator from data, and this is today's main topic. Koopman operator is an infinite linear operator defined on the observable space of the dynamical system. It is defined as a composition operator with a flow map of the nonlinear dynamical system. So the flow map basically maps the initial condition to the system state after time t. And therefore, the Koopman operator acting on the observable f tells you what's the observables after time t. And we refer to Koopman analysis as the spectral decomposition of the Koopman operator. Basically, it decomposes the evolution of observables into three parts: the time average part, the point spectral part, and the continuous spectra. And in this talk, we'll only consider the first two terms while neglecting the third one. Third one corresponding to the fully chaotic part, which is fully incoherent. Today, we're not going to talk about this. And even with the first two term approximations, which we refer to as point-wise spectral approximations, it is enough to build a finite dimensional linear system in the lifted coordinates provided by the Koopman eigenfunctions. So as an illustration, as you can see, this idea of Koopman operator is basically you need to find these nonlinear transformations that maps the original nonlinear dynamical system into a linear one. However, it is not easy to find such Koopman operator analytically, and the existing literature on these analytical approaches restricted to using a data-free approach that leverages the multi-scale analysis directly on the Navier-Stokes equation. While the data-driven approaches leverages either dictionary-based methods or neural network approaches, which has been successfully applied to a wide range of problems. However, existing neural network methods on the right is prone to poor local minimum, and training such a neural network is very expensive due to the non-convex optimization nature. For the DMD and SPKDMD, as been shown by Chen in 2014, that they are not suitable for strongly transient nonlinear flows. For EDMD and KDMD, it contains too much eigenmodes that doesn't evolve linearly. This is also the problem for DMD as well. and the lack of a proper procedure to selecting hyperparameters, and there's no sparsity-promoting algorithms available. So what we want is we want sparsity so as to increase our interpretability. We want accuracy so that the modes are very close to the Koopman, and we want they are going to be fast, so we would prefer convex optimization over non-convex optimizations. So the question is, can we find an informative and accurate Koopman invariant subspace with dictionary-based algorithm? So in this talk, I propose a framework called SPKDMD that is able to find an informative and accurate Koopman invariant subspace. The general idea is to first consider an a priori analysis on finding the optimal parameter, then apply distributed POD to obtain a lower dimensional subspace, and then we apply the standard EDMD and KDMD or scalable EDMD. Then we perform a mode-by-mode maximal linear evolution error analysis to filter out the wrong modes that didn't evolve linearly. Finally, we choose a trade-off between reconstruction error and linear evolution error. And finally, we consider a sparse reconstruction of system state from accurate Koopman modes. Basically, those Koopman modes are kept after filtering with the following multitask learning, which is a convex optimization problem. Our code and manuscript are available online. One may wonder how our algorithm is related to previous methods. Indeed, we showed that our algorithm is actually a generalization to previous methods. Previous methods including sparse-promoting DMD and empirical criterion, and under the assumption of linear features and fixed Koopman modes, our framework reduces to the original Sparsity-promoting DMD. Under the assumption of infinite small learning rate, we proved that the above empirical criterion is performing one-step proximal gradient method optimization to the objective of a Sparsity-promoting DMD. As a summary for the three methods, our framework contains no empirical bias, and it doesn't fix the modes such as in DMD, so that it has more degree of freedom to fit to optimally reconstruct the system state. And also, we have an error analysis to filtering out those wrong modes. So let's apply our algorithm to a very classical cylinder flow problem. Note that our data contains the whole phase from the unstable equilibrium to the limit circle. Our algorithm shows accurate reconstruction performance against the ground truth data, and you can easily see how we select truncations based on this reconstruction plot and linear evolution plot. So basically here, the red lines corresponding to the reconstruction versus the number of modes you kept, while the blue lines corresponding to the linear evolution error of each mode, and we order them such that it will be always increasing. And as we can see here, we're selecting the optimal mode selections, similar to SPKDMD, where we follow the Occam-Razor principle, that we consider a model such that it basically is on the elbow of the arrow plot. Finally, we kept 30-ish modes out of 250 modes, which is a great reduction of order in the Koopman operator. Let's look at the eigenvalues. We observed similar trends in previous works in 2013, where you can see this clustering behavior of eigenvalues are shown here. And now let's look at some nice animations in unextracted flow fields where such long-time coherent structures are displayed and a posterior predictions matched well with the ground truth. Further, we analyzing the effect on how parameters such as Reynolds number affect the Koopman model space. So what we do here, we're extracting the phase from the stable Koopman decompositions. Then we draw the isocontours. Then we superimpose all the isocontours in time, such that you can form an envelope of the model shape. And then we stack them all together for 3 different Reynolds numbers. We can see an interesting trend that as Reynolds number increases, the head of the envelope increases and the tail becomes more parallel to the free stream. And also we observe there's a discontinuous line in the U velocity component for the first harmonics. And we found that such discontinuous line becomes more and more flat and close to the center line of the geometry as the Reynolds number increases. Moreover, note that if you superimpose the first and second harmonics, which is an antisymmetric and symmetric modes, you will end up with a phenomenon like vortex shedding. So this is how vortex shedding is decomposed in the views of Koopman operator. To fairly compare against a Sparsity-promoting DMD, we first fit the standard DMD with 200 POD modes, then perform SPKDMD to truncate to the same amount of modes as our algorithm has. One can see the blue lines corresponding to the SPKDMD, which perform worse than the red lines, which is our algorithm. Look at the eigenvalues. A simple DMD with 20 POD coefficients doesn't perform very well. Note that our algorithm is using the first 20 POD coefficients only because it almost captures more than 95% of the energy. And as we can see here, both sparsity-promoting DMD and our framework captures stable modes very well, but it doesn't capture the amplitude very well. As you can see here, it is a little bit off. The amplitude, and moreover, in initial condition is way off. As we can see, we should expect there will be a significant discrepancies in the initial conditions if you obtain the model from SPKDMD. Now let's take a look at the second examples, the ship air wake problem. Ship air wake problem can be critical for and important for the safety of helicopter landing on the ship. Here we consider a transient flow dynamics from abruptly side wind. The simulation is performed by unsteady runs. Using our algorithm, we are able to identify 3 important coherent structures from the side deck and from the back of the superstructure and behind the funnel. Well, sparsity-promoting DMD here, basically corresponding to the blue triangle here, it gives you all the modes on the nearly on the unit circle, but 30 out of 56 of them are unstable, which means they actually blows up at future time step. This representing a really bad mode decompositions and for reducer modeling purposes. It does not give you the most sparse representations. For example, only 3 dominant modes here. It doesn't give you that. What's worse is it also gives you some modes that's not stable, which you don't want to use it for predictions. And so summary, we have proposed a sparsity-promoting framework for the EDMD and KDMD for extracting informative and accurate Koopman Invariant Subspace for a nonlinear dynamical system. As a general extension, we revealed the analytical relationship between our framework, SPKDMD, and empirical criteria. Our framework is model agnostic, which means it can be applied to any other Koopman approximation methods, for example, the time delay DMD. And we have shown 2 examples in fluid mechanics demonstrate superior performance over sparsity-promoting DMD. Linear feature from DMD is not reliable for extracting Koopman operators for transient dynamics, for example, the flow instability that we have already seen. And this is actually also come from 2014 Chen's paper. And moreover, sparsity-promoting DMD modifies only the amplitude. Therefore, there will be a mismatch in the initial condition, while SPKDMD, which is our framework, modifies modes, which is more flexible than the only optimizing the amplitude. Our code and papers are open source online. Please take a look. And thank you for watching.